Optics is about properties of light and optical devices. And historically, there are two competing theories of light. And one, probably the most intuitive, is treating light as tiny particles traveling from a light source in all directions. Because we know a lot about particles. If we give it supply some velocity and don't apply any forces, it just travels along a straight line with constant velocity. When a particle encounters an obstacle, it bounces off it, and we know what's happening to the momentum. Yeah. In ideal situation, the magnitude of the momentum stays the same, and the angle before and after again is the same. So in this situation, each light ray we can think of as a trajectory of a specific particle. For example, here, the laser pointer. Yeah. Well, a laser pointer is a light source. We can see this light. And if I move again away, we can imagine there is a particle traveling in that direction. We actually can see this trajectory. Straight line. That's what we call a light ray. And we can use this idealization to describe different situations. For example, I am aiming straight down, but you can see the spot over there on the screen. Why is it happening? Well, there is something here, not a black surface which absorbs everything, a shiny one which reflects light. So in this situation, this mirror just changes the direction of the ray. Yeah. Again, we can see approaching ray, reflected. We call it incident, reflected. And this is only one of many situations where we can use light rays to analyze whatever we want to analyze. Today we start from talking about simple plane mirror. A plane mirror looks like this. Well, a regular surface has a lot of bumps on it. So for each individual ray, we always can apply the law of reflection. The angle before and after reflection is the same. However, if we have a bumpy surface like that, rays which are initially parallel to each other are not parallel anymore after they encounter the surface. We call it a diffuse reflection. A mirror doesn't work like that because we actually make it very, very smooth, so it's not so bumpy anymore. And in that situation, for a mirror, for a good mirror, rays which are initially parallel stay parallel after the reflection, like in this simple demonstration. This is a mirror. I have 4 parallel rays traveling towards it, and after the reflection, they stay parallel, remain parallel. So this is a specular reflection, not diffuse reflection. But more importantly, do you see any light behind the mirror? No, remember that. There is no light behind the mirror. And this is my first question. Based on this experiment. Let's say we have a mirror somewhere here, and there's an object placed to the left of the mirror. Can be an image, a real image of that object found somewhere on the right. All right? Let's test the system. So far, so good. Well, by asking this question, I assume that you read already, well, at least some pages from this chapter, and you know what a real image means. Real, actual. So almost the third still thinks yes, which is not good. But most of you are right. The right answer is no. Because, first of all, what is a real image? Again, let's take a look at this example. A real image, by definition, is an image which is formed by actual light rays. So the location of real image can be only there where actual light rays are presented. So if I want to see a real image, I don't need, in general, to use my eye. I could use a photocell which detects light. Instead of a photocell, I could place a screen. And if I see light on the screen, that means a real image could at least be formed over there on that screen. If I place the screen behind the mirror, since there is no light behind the mirror, a real image cannot be formed there. Because again, remember, the real image must be formed by actual light rays. However, if you look in the mirror, you can see stuff. Why? Well, it's important to understand that there is another optical device involved in this particular phenomenon. When you're looking around, you're using your eyes. And eyes is a lens. And we're going to talk about lenses in a couple of classes. So far, it's not very important. We just need to remember, in a region with no light, there is no real image. Now, so the law of reflection is very simple. If you have incident ray and reflected ray, the angle of incidence is equal to the angle of reflection. That's only one part of the law. Another part of the law is that they should form a plane. They belong to the same plane. The normal, which is perpendicular to the mirror, and both rays. For example, let's say this is an incident ray, and this is a mirror. So incident ray, normal, that's the angle, 30 degrees. And after the reflection, can this rod represent reflected ray? The angle between the normal and the ray is 30 degrees again. No, it can't, because the ray, another ray, and the perpendicular should belong to the same plane. They can't just bend away. So the law of reflection has two parts. Well, second part gives us way to calculate things. For example, we can calculate location of the image, the size of the image. If we replace an eye with a screen, will the image be formed? So when you're looking in the mirror, you see this object. If instead of you, there's a screen is placed, do you think on that screen the image of this object is going to be formed? Yes or no? It's a good question. I invented it. Well, what did I do? The first condition for a real image to be formed is that it has to be formed by a real light. Now, there is another important condition. Let's say this is a bulb. It's a point source. And this is a mirror. So this ray is traveling away from the bulb, and now it is getting reflected from the mirror. How? Well, the law of reflection tells us how. We should draw a perpendicular to the mirror, and now we can measure, we can use a protractor, the same angle from the normal, and that's supposed to be a reflected ray, right? Now, let's take another ray from the same source, like this one. So if you look at the reflected ray of this guy, smaller angle, this is how it's going to be reflected. Do these two rays converge? Or do these two rays diverge? Converge or diverge? They do not converge. So, an image of the point, an image of the dot, is supposed to be a dot. An image of a, I don't know, clock supposed to be clock. So the image of this bulb is supposed to be a small bulb, but that's not the case. So having these rays in this region is not good enough yet to form an image. These rays are supposed to be converging in order to form an image. Even if you place a screen over here, it's still not going to help. We could form an image for this situation by using an eye, which I said again, a lens which converges light on a retina. So we don't talk about this. But we have to remember, so first of all, if a real image has to be formed by real light rays, and those light rays, when they travel from a point source, also have to be convergent to a point. And that's not happening here. However, if we trace the extensions of those rays behind the mirror in the dark region, the darkness, in that case, these extensions do converge. So, a real image cannot be formed, well, without eye here. However, here in this part of the darkness, an imaginary or virtual image of an object can be formed. However, to see that virtual image, we need a special device, an eye. To see a real image, we don't need a special device. We can use a photocell or a screen. So, let's for this example, this object, as any other object, has a lot of points. Well, of course, there's a sun. The light from the sun is getting reflected from this figure in all directions. So from this point, for example, on the top of this little figure horse here, light getting reflected in all directions, but only rays which go to the mirror are important to us. This ray is getting reflected. Its extension is getting behind the mirror. Another ray from the same point, again, is getting reflected. Well, getting reflected like that. This extension goes behind the mirror. We don't need this. This ray is getting reflected. This extension goes behind the mirror. So this point represents the image of that point. We call it normally sometimes O and O prime. And theoretically, we would have to find the image of each individual point of this figure. Yeah. But if we want to figure out the size and the location of the image, we just need to consider 2 points, the top and the bottom. For the bottom one, again, well, we don't have to use always these particular rays, they reach the eye. Yeah. We could use, for example, a ray like that. The ray which is perpendicular to the mirror should go straight back, and that's going to be its extension. And we know that this image is supposed to be, well, here. So now we can see 2 facts. The first fact, for the plane mirror, the size of the image equals the size of the object. And second fact, for the plane mirror, if the object is upright, the image is upright. So the plane mirror doesn't change the orientation, keeps the orientation. Now we can list, well, that's the better picture. We can list all the features of the images formed by a plane mirror. What kind of features? Number 1, it's a virtual image, it's not a real image. We need an eye to see that image. Number two, the size of the image equals the size of the object. Number three, the orientation of the image is the same as the orientation of the object. And, well, if we apply a simple geometry, we can prove mathematically that the location of the image is symmetrical to the location of the object. The distance from the image to the mirror equals the distance from the object to the mirror. Or, shortly we say, object distance has the same magnitude as the image distance. And these parameters, size, orientation, virtuality, reality, and distance, we're going to be using again and again and again for many other situations. It's the simplest case, a plane mirror. We're going to talk about spherical mirrors. We're going to talk about lenses. And for any optical device, we always start from an object and eventually end up with an image. And we have to characterize that image. And we're always going to be repeating the same parameters: size, orientation, virtuality or reality, distance. Well, now, when an image is virtual, when the image is virtual, it means it is not formed by actual light rays. It is formed by extensions. The image distance is negative. It's an agreement. So the magnitude is the same. However, the object distance is always positive, but the image distance might be positive and negative depending on the situation. For the virtual image, it's negative. Now, when the object has the same size as the image has the same size as the object has, we say that magnification equals 1. And the magnification also could be positive and negative. It depends on orientation. When the image has the same orientation as the object has, the magnification is positive. Well, now we're just going to answer different questions, solve some simple problems related to this topic. Here, we have two questions to answer. So this set of numbers for the first question, that set of numbers for the second question. This is a wall, and you have a light source. Let's say a laser. Yeah. So it travels toward the mirror, getting reflected, and this photocell registers that reflected ray. What we know is that this angle between this ray, which is vertical, and the reflected one is 40 degrees. First question, find the angle between the mirror and the vertical. All right, start working, please. I'm going to ask you this question soon. Very soon. So what you're supposed to do? You're supposed to draw a picture, and you're supposed to show the normal to the mirror, because the law of reflection involves that particular, I'm not starting collecting your answer yet. So there is a missing element here, the normal. You should add it to the picture. Oops. I don't like it. Let's try again. The distribution is too not even. And I suppose, unfortunately, you can't enter any number, any two-digit number, right? Even if you want it, like 11 or 12, it's impossible. Again, that's really strange. Well, so this is the incident ray, reflected ray. That's supposed to be the normal. This angle is supposed to be equal to this angle. So if this angle equals 40 degrees, the value of this angle is what? Supposed to be 20 because of the law of reflection, because law of reflection says this equals that, so alpha equals beta. However, alpha plus beta equals 40. That's the actual mathematics behind this question. Yeah. And now this is a normal, which means this angle is supposed to be equal to 90 degrees. 90 degrees. The angle we are looking for is this angle. This is our picture. This is 20. This is 90. So the angle we are looking for is 70. 70. Okay, that's what's supposed to be your answer for. Because you cannot enter 14. All right. And the second question. If you want to hit the second photocell, so you have to turn the mirror. Turn the mirror, yeah? So by what angle do we need to turn the mirror? Well, I'm going to ask, let's just do it together. So, to turn the mirror, your new angle is supposed to be equal now 40 plus 20. It's been 40 plus 20 more, 60. That means if you turn the mirror, your new normal is supposed to be directed like that. Well, I can't draw it to a scale, something like this. That's a new normal. Not good enough. These angles are supposed to be equal 30 and 30. Well, I'm not good at drawing. And your old normal was like this. Your previous normal was at 20 degrees to the vertical. So, from 20 to 30, you should make a turn by 10 degrees. Any question? So, the law is simple, but sometimes you just have to think through the application of this law with the normal, with the angles. Another question. This question I'm going to ask you. What is happening? That's the mirror. You see, it's kind of short. This is a bulb, the source of the light. So, first question. Which of these locations represent the location of the image of this source? Well, 5. Neither. Okay? I should have 32 responses. So someone either fell asleep or doesn't have a clicker. If you don't have a clicker, raise your hand. So someone fell asleep. All right. I don't blame you. Well, it doesn't matter, how big a mirror is, it still forms an image. Well, the brightness might depend on the size, because if you get a lot of the light concentrated at one place, more energy, more intensity, if the small portion of the light reaches some point, less intensity, not so bright. However, oops, too soon. Here, still, this mirror would reflect some light. And again, this light would be reflected like this. This ray would be reflected something like this. I really need to use a protractor, a ruler, to draw an ideal picture. What we see is that these rays would, well, have their extensions converge somewhere. Where? Well, as we know, the image is symmetrical to the object. So if we had a large mirror, not broken one, like this, that mirror would form an image at exactly the same distance to the mirror. Yeah? So for that mirror, we would have to just draw a perpendicular and measure the same distance, and that would be the location of the image. Well, of course, it's a virtual image. There's no real light over there. However, even with the broken mirror, without this part, we would still get some, well, rays reflected in the same way. So we would still get the image toward here, the virtual image. Now, here. Well, this is the surface of water. Actually, you don't have this question in your handout, because I made it up just yesterday night, and that's been printed out yesterday morning. So, and this is a periscope. So it's traveling underwater towards this pontoon. And let's answer the first question. This distance is 10 meters. The distance between the object and, well, this mirror is 200 meters. How far is the image away from this mirror? of the periscope. So what do you think? These are your answers. Well, what does it mean the image is 200 meters away? It means it's over here. What does it mean that image is, well, at more than 200? So it's over here, less, somewhere here. So these are your choices. You see, even very, very simple law might generate many different and not so obvious problems. We can stop. More. More people vote for more. And that's correct. Well, this is the case, very rare case, when a smaller picture actually works better. Let's see. So, what do we get? The first mirror, the object. We just answered the question about the image formed by this mirror. It's like a broken mirror here. So, where is the image? We can extend the mirror, and relative to this mirror, the image is supposed to be here. We know it's supposed to be 90 degrees, 90 degrees. We actually have to assume that a regular periscope has a mirror at 45 degrees. It's not said, but it's a standard, that's 45 central. If this is 45, so that's supposed to be 45, this is 90. That means this side is supposed to be equal to this side of this triangle, and that's supposed to be equal to this side. So this distance, let's say, S is supposed to be equal to that distance, S. Pure geometry. Now, second mirror. What does it do? Well, it forms an image of an image. That's what it does. So again, we can extend this mirror, and for this mirror, this point becomes an object. And if we want to form an image of that object, again, we have to do the same procedure. We can draw a perpendicular to the mirror and measure the same distance. That's supposed to be the image of this image with the image of this object. So this is the image. So if you have your eye here, you're looking at the virtual image located there. So now, again, geometry says that this distance, let's say L is this, L prime, supposed to be equal to this distance, which is L plus S. So S is the distance from the object to the periscope. The distance from the image to the periscope turns out to be equal object distance, this one, plus the size of the periscope. So more than 200 meters. My second question was about speed. How fast does the image move? Well, in that case, of course, they travel the same distance over the same time. So velocity for both is supposed to be equal. And another question. It's about mirror. Do you think this mirror is big enough to, well, for you to fit your image completely in it? No, it's too small. However, if you walk in a, I don't know, store with a wall mirror, you can see yourself completely and even more. So of course, it's supposed to be somewhere critical size. The mirror, which is just enough to fit your, right? Have you seen it in the movie? Well, I've got a big mirror like this. So could you please try to look at it? Do you see yourself completely? Just walk. Do you see your top of your head? Can you get closer? Do you see your feet? So you see everything. Well, and you're supposed to. Thank you very much. I need a really tall person. Who consider yourself tall? Yeah. Who you get? Men behind two ladies. Try to fit yourself. Well, not yourself. It would be hard. But your image. What? Can you make you see completely from the top to the bottom? Well, you can cheat. So you see the same mirror, different people. So size of the mirror matters. And this is the question. Well, actually, two questions we have to answer. First of all, what is the minimum size of that mirror you can use to fit completely your image? And second, how it's supposed to be placed, because it also matters. So I'm going to give you a minute. You should have a similar picture, and that's what you should do. So this is you, from the top of your head to the floor. That's your eye. Draw an image of your top. Draw an image of your feet. So, there again, easiest way to draw an image of something is this. This is the point, the image of which you want to draw virtually. So what do? You know that image is supposed to belong to this perpendicular, and it should be exactly the same distance from the mirror. Where is the image of your feet? Well, the same thing. Somewhere here, at the same distance. The distance from the object to the mirror equals the distance from the image to the mirror, or the plane mirror. So we don't have to use always the law of reflection. We can use the fact that image is symmetrical. Now, so this is your image. What about light rays? Well, of course, in real life, light should be traveling from this point, reach the mirror, and get back to your eye, like this. However, so where is this point? The easiest way is just draw a line from the eye to the image. Because we know the extension of this ray should travel toward the image. That's it. So if you take a ruler and you draw this line, that gives you immediately this point. That's a critical point. You don't need anything above it. You already see the top of your head. What about the bottom part of the mirror? Well, again, if you connect these two dots, this part represents the actual light ray from your feet towards your eye. This part represents the extension of this ray, which is supposed to again cross at this point, at the location of the image of the feet. So, anything below this doesn't matter. Now, please answer your question. Well, I assume people who answered correctly just had drawn more accurate picture, because it's just about picture, good picture, that's it. This is a good picture. If you look at the good picture, you see this part is cut off, this also. So you can even just count squares. Your height, 1, 2, 3, 4, 5, 6, 7, 8 squares. Mirror, 1, 2, 3, 4 squares. 8 versus 4. So the mirror equals exactly a half of your size. Well, of course, you can prove it geometrically, but you have to use in that situation the law of reflection. You have to say this angle equals this angle. That means this side equals this side of this triangle. So you divide this in half here, and you divide this side in half here. So you divide the whole image in one half. The mirror, in order to fit your full image, it must have at least certain size. Plus, in addition, it should be placed at a specific height. So here, in this picture, you can see if this is your eye. Well, first of all, for the plane mirror, the image must have the same size and be at the same distance from the mirror. So that's supposed to be your image. So this is how you should see your feet. This is how you should see your top of your head. This is a real array. That's an extension. And this is the size and the location of the mirror you can use. And for example, if you want to use a smaller mirror, or you need to move it up or down, well, in that case, you can see only a part of your image, and there's a problem when you use a mirror which is 1/5 of its original size, and in that case, so if you cut 4/5, so now there is no this part of the mirror. That means, well, this is the person. Oops. You can see only this part of the whole image. And this is how much you cannot see anymore. And if the new mirror is located at the same height, but the size is 1/5 of the original one, in that case, you can see only 1/5 of the whole image. And this is how much much you cannot see.
Well,
this is another example how a mirror forms an image of an image. Yeah, the question was how many images would the person see in a mirror like that. So this is an object. This mirror forms an image. This mirror forms an image. However, again, well, we can say that this mirror forms an image of this image, and that's how we can get 3 images, and we know again the distance from the object to the image should be equal to each other. We could use these rays to actually prove that the third image is located right here, you see. This image is formed by rays which experience 2 reflections from the first mirror, from the second mirror. This image is formed by rays which experience only 1 reflection, like this, for example, and that. Well, if you have more mirrors, you can apply this idea again and again and again.